Hey everybody. Okay, now that we've gotten everything unpacked, um, I want to go through a couple of things. One is taking a little bit closer look at the components we unpacked before, and then we want to work on downloading and installing the waveform software so that we can operate the Analog Discovery 2 and determine whether or not your PC is going to be able to drive it. Um, in the past, with older PCs in the lab, we've had a problem with some USB ports um, not being able to supply enough current to drive it. And so we'll determine that today. But the first thing we'll have to do is install the waveforms software. Um, and then once we do that, we'll learn how to use the multimeter and the breadboard. And we'll build a circuit. We'll measure some resistance. We'll measure some voltages, record them, and do some calculations. And then maybe if we have time, we'll play with some of the other components in our kit. Okay? All right, so let's get started. So let's go down here and change the view. Okay, so this is a list of all the components that were in that kit, and I guess I want to underscore some uh, some terminology issues. So these things here, this ribbon cable with the um, pointy ends on one side, the male, so that's a male end, and a female end on the other side. This is what they're calling a DuPont wire. Okay, and they call it 20 pieces. It looks like it's one piece, but each one of these can be peeled away and used individually if you don't want to use them as a bus. Or if you have a group of four signals, you could rip off a group of four of them, and each one will have a different color so that you don't get you keep your signal straight on each side because they'll be color coded. Um, and what else? We know what that is. The button switches. Well, there are several types of button switches. Actually, two types. One is called normally closed. One is called normally open. And some switches are built to be able to do both. And there's no data sheet provided for these switches. So maybe we'll get a chance to play with that and figure that out. The um, the thing I thought was a microphone in the original recording was wrong. One of these, so both of these little cylinder things here. So both of these little cylinder things here, both of them are buzzers, but one of them is an active buzzer, which I assume means when you apply a voltage to it, it will play a tone. And the other is a passive buzzer, which I assume is a type of loudspeaker. And we'll play with those and determine what they do. And then the photoresistors, the thermistors, precision potentiometer. I labeled all these things as transducers, even the potentiometer, because the potentiometer responds to our mechanical manipulation. So I'm going to call that a transducer. And then there are diodes and transistors, and they have part numbers, thank goodness. And then the capacitors. So just remember the ones in the cans, the electrolytic capacitors, they can be dangerous if you don't connect them correctly. And then there's a whole bunch of LEDs, including like the two that had multiple leads, not just two, and those are RGB LEDs. And then all the resistors. And I put a little notation here that resistors limit current and capacitors limit changes in voltage over time. So we'll talk about capacitors like much later in the semester um, because they do change the dynamics of a circuit, meaning that how fast things can occur. Okay, so first thing we want to do is download and install the waveform software. And so to do that, you can Google Digilant waveforms. So I Googled here Digilant waveform software download, and you can click on this link. And when you do, you get here, and then from here, you can choose your operating system, Mac, Linux, Windows, or ARM, and download the software. So I'm on a Windows system, so I'll click Windows, and that software should download. And it's a standard install process. So I don't think there's much to talk about there. Once you've installed it, you can run it. And so let me go over and run my waveform software. And when I do that, it tells me no devices are detected. So let me see if I can't get that to happen in my window here. I guess I can't. So I'll move it on over. So the window looks like this, but we don't have anything connected to it. So there's a workspace, and we can save our workspace once we've gone to the trouble of building a whole bunch of stuff. We want to save the configuration, and then there are settings and options, and we'll go through that as we make progress here. One of the things I wanted to point out, before we go on, is that is this resistor color code here. So the resistors we have are strangely colored. The body is strangely colored, and it makes it really difficult for me to be able to determine what colors are in the are painted on the resistor. Let me go to up here and go to the bench. So if I go to the bench, there's my camera, and from this image I can hardly tell like what colors the bands are, but your eyes might be better than mine, and you may be able to tell. I put it on a black background because my camera seems to focus better when the resistor's on a black background. And so if we go back to the screen here, you can see this is how the color code works. So each color represents a different digit. White is 9, all the way down to black, which is 0. Brown is 1, etc. And if we take a look at one of our resistors, so I took an image so that I could blow up blow it up and see the colors clearly. So looks like there are 5 bands on this resistor. This band here is the band that determines what the tolerance is. If we go back to the oh, we're in the screen already. So if we just go back to here, the 4th band is a tolerance, and it could be 5% if it's gold, 10% if it's silver, and then there are others, but gold and silver are usually the ones you see. All the resistors in our lab are 5%, and I think from looking at the resistors here that that could be gold or that could be silver. See, when you get old eyes, it's like hard to know. If that's silver, it means it's a 10% resistor. Anyway, this is the first band and it's green, and this is the second band. Oh, I see. So yes, so this is greens, that represents 5, and that's a 1, and that's a 0, and we're going to add 1 0 after that. So 5 1 0 0 is 5100 or 5.1 k ohms. And you can use a tool to figure this out. I certainly don't expect everybody to memorize the color code. If you search for the color code, you will find that there's a color code calculator, and then there's also a color code table here. And so let's go for a 5 band because that's what we have. Okay, 5 band. So now we have a green, and we have a brown, and we have a black, and we have another brown, and the tolerance, I don't know, it's your guess or my guess, but I'm guessing gold. The tolerance is 5%, but we'll find that out as we experiment with our resistors, how far off they are. So anyway, that's the resistor color codes, and hopefully your young eyes are better than my eyes, and you'll be able to just look directly at the resistor without having to take a picture and zoom it up, or better yet, come up with your own way of determining the resistor values by keeping them in separate bins or something, but or measuring them. Let's do that. Okay, so measuring. Before we do that, we better check on our waveform software, right? So let's do that. So here's my waveform software, and it's running, and I have not plugged my Analog Discovery 2 into my machine, so I'm going to do that now. Here we go. Boom. I plugged it in, and I got the happy beep, and here I get a message. It says, it was detected. Do you want to connect to it? Yes. So I click on that, and we'll see what happens. Oh, am I in the wrong window? Yeah. Click on it. Yes. So in principle, I'm connected to my Analog Discovery 2, and I'm looking for some indication on the Analog Discovery 2 that I'm actually connected. a light or something. But let me move to the bench, and you can take a look too. So move to the bench. Okay, let's get these resistors out of the way. And here's how the Analog Discovery 2 is connected to the breadboard. And I'm going to zoom out, and I'm looking for some light, but I don't see anything. So let's just try to do something and see what we get. So we'll go to the full bench. Now we'll go to the full screen, and here we are in the waveform software, and here we're in the Welcome tab. And in the Welcome tab is where we choose the things that we want to do. So we're going to choose a power supply. So recall that we have two power supplies. One is a positive supply and one is a negative supply. And we won't be using the negative supply very much, if at all, this semester. So we can set the voltage here on the right. There are voltages we can choose, or we can just type something in. And this says it's ready, and that says it's off. And then there's a master enable up here. So you have to have two things on in order to operate the supply. We're not going to use this negative supply, so but I'm going to leave it ready. Yeah, I'm going to leave it ready anyway. And so master enable is off, so I'm going to turn that on. So of course nothing happens. But what we want to do is take a look at the bench now. So here's the bench. We've enabled the power supply, and so because we've enabled the power supply, V plus should have 1 volt on it, and V minus should have minus 1 volt on it, and those things are with respect to ground. So remember our digital voltmeter, our digital multimeter. I can fold out this back piece so that it sits up at a nice angle that I can easily read. And let's take a look at, let's put it here. And let's take a look at the voltages we get. Now we have to set it to the left, turn to the left to measure DC volts. So that's the icon for DC volts. That's the icon for AC volts. We don't want that. We want the icon for DC volts. And we know we're going to measure 1 volt, so we could put this in the 20 volt range, and 1 volt should be clear to see. Now, we need to touch these probes to something that's metal. And although the header has some metal, I'd like to avoid touching the header with the probes, just because the probes are fat, and it would be easy to inadvertently make a connection between two of these pins. So so I'd like another way to do that. One way to do it is to take advantage of the fact that we have these headers. that we can use to stick in the holes. Now, of course, the header doesn't like fix very much because, in fact, the headers are just as close together as the pins that are in the breakout board. So no advantage there. If we were in the lab, we would use wires to make connections between ground. So ground is going to be this triangle here. Ground is going to be this triangle here. Third pin down. I'll put a black probe in there and then a black wire in there, and then the orange wire I will put in V plus, which is right next to it. And again, if we were in the lab, we would have clips that we could clip onto here to make the measurements, but we don't. So instead, I'm just going to hold these probes to the wires. And when I do that, you can see that my meter shows I have 0.99 volts. So no measurement we make is going to be exactly what it's supposed to be. There's no such thing as being exact. If you have enough decimal places, you will always be off of 1.00000000. Okay? So that's on the plus side. And on the minus side, I see minus 0.99. And it sort of varies. It sort of flips between minus 0.99 and 1.0. So that's very accurate. Let's see if we can change that. So I'm going to go back to our software and change plus 1 volt to plus 5 volts. And go back to the bench and make the measurement. So black to black, red to red, and now it says 4.98 volts. So that's pretty darn good. 4.98, 4.99, pretty good. And on the other side, where we should have the minus volts, that should still be minus 1 because we didn't change that. Okay, minus 1. So you ought to be able to perform this experiment to demonstrate that you can control the power supply of the analog Discovery 2. That's the power supply. Now, the way these windows are laid out, I can do things like I can take this and I can drag it somewhere. Let's see, can I drag it somewhere? No, I have to go to Window, Settings, Options. So a couple of things. You may have a dark theme. It's not going to show up in this window, but it will show up in other windows. If you have a dark theme and you set up an oscilloscope and you want to print that out, you'll be using all of your black ink. So it's better to have that as light The style window vista is fine. The instrument window is docking, but you can have them as separate. So now my power supply window, which really doesn't need those really huge buttons, I can shrink that down to something quite small. Put it in the corner and be able to turn the power supply on and off like this. But now that I've tested that negative supply, I can turn that off and just turn the 5 volts on and off like that. Everything else is good here for the moment, but instrument windows being separate, that can be really helpful. Okay, so there's my power supply, and we can use. So if I go back to the welcome window, we can use the Analog Discovery 2 as a voltmeter. And so when I do that, now I have 2 channels, channel 1 and channel 2. And I could connect channel 1. So let's go back to the bench. So channel 1, let's even zoom in a little bit here. Okay. So remember, channel 1 has a plus input and a minus input, and these measurements we'll be making right now are going to be what we call single-ended. And so the minus side of the channel 1 input gets connected to ground, and we can do the same thing with the minus side of the channel 2 input. Channel 2 input minus side gets connected to ground. And now we can connect channel 1 to V plus, and we can connect channel 2 to V minus. And if we go back to the waveform software window, so here's here's the voltmeter. What happened to our power supply window? It must have gone underneath all of this. Yeah. So let's do that. And let's take this and minimize this. And so now we just have our waveforms welcome window, our voltmeter window, and our power supply window. And let's turn everything off. I'll turn those 2 off, and I'll turn master enable on. So now when I run, this is going to work like a voltmeter, and what it's seeing is I have the power supply shut off, so channel 1 shows a very small voltage, and channel 2 shows a very small voltage. Again, ideally, in the ideal world, it's 0, but because it's a measuring instrument and it has there's some error associated with every measurement. Instead of 0, we have 0.007 or 0.006. Okay, so now if I turn the power supplies on, Channel 1, because it's connected to the plus supply, should go up to 5 volts, and channel 2, because it's connected to the minus supply, should be minus 1 volts. So let's see. Turn it on. Oh, what happened? So there was an error message that popped up there. Let's take a look again. Stop due to an oven. Stop due to an oven. Use an auxiliary supply to increase the power output capability. Yeah. So I'm not sure what it means by due to an oven, but now the point is that I need to find another USB port to plug this into, because the USB port I have it connected to is not working. So let's stop that. We've stopped the power supply, and what I want to do is save the workspace. So I'm going to save the workspace, and instead of calling it default, I'm going to call it voltmeter plus power supplies. Save. Okay, now when I unplug this, the software is going to complain. Yep, it's going to say communication with the device failed, because now it's no longer connected to a USB port. And now I'm going to connect it to another USB port on my computer. So let's see what happens. So now I have it connected to another USB port. You know, the interesting thing is that that was actually connected to a powered USB hub. So I'm not sure why that is, but here's my analog discovery discovered again, now that it's plugged into another port, and I'll select that. And we'll see what happens. Ooh, device configuration failed. Needs at least that amount of power, and I don't have it. Okay. So this is bad news. But again, because let's see each other here. So because I'm doing all this recording, I have probably 10 devices connected to my USB ports. Even like the monitor that I was showing you the waveforms on, that monitor is connected and powered by the USB ports. So okay, I'm glad you got to see that, because the problem had nothing to do with my ports. The problem had to do with I was using this USB extension cable, which has wires inside that are thin and unable to provide enough current for the device to work, or at least the device perceived it that way. And now that I'm plugged directly into my USB port, all my USB ports work. So that's the lesson there. Okay, so let's go back and take a look at what we got. So recall, we connected channel 1 to the positive supply and channel 2 to the negative supply, so we could monitor monitor them, let's go down to the screen view, and this is where we are. This is our voltmeter window, and this is our power supply window. We turn on the voltmeter, we see very small voltages. We turn on the power supply, boom. And so channel 1 that we have set for 5 volts is actually 5 thousandths of a volt higher than 5 volts. And channel 2, which is connected to the negative supply, which is set to -1 volt, is now 991 millivolts, which is 9 millivolts, 9 thousandths of a volt, smaller than -1 volt, which is perfectly fine. Okay, and we're just going to ignore these true RMS and AC RMS for a while. But DC is the important thing we're looking at. Okay, so so now we've made measurements of power supply voltages, and we can go ahead and change the power supply voltages. So if we made this, let's say 4.1 volts, boom, channel 1 changes to 4.1 volts, and if we change the negative supply from -1 to, let's say, -1.7, boom, that gets changed right there. Okay, so so that's how to use the voltmeter and the power supply on the Analog Discovery 2. Now let's think about building circuits. So I'm going to turn that off. I'm going to stop that, and we're going to move on to our window where we're talking about circuits. So we downloaded and installed the waveform software, and we checked to see if it works with the computer, and it did not, because I had a cable problem. And so we used the multimeter to measure voltage, but what we found was that there's an issue using the probes, in that you don't want to risk connecting two electrical points together on the breadboard, and the solution to that is to extend those points using wires, or to use clips that I neglected to provide, and so at some point I'll purchase those clips and try to get those clips to you, because it's a lot more convenient to use them. Okay, so let's measure resistance and voltage, and talk about what's involved with that. So I'll go to the bench. And we'll zoom out. So one of the issues with measuring resistance is it's easy to measure resistance, but to get an accurate resistance measurement, it has to be done correctly. So you can get an approximate resistance measurement easily, but to get an accurate one takes some technique, and it's important to use that technique. So first of all, our voltmeter has got to be, well, I want you to see everything. Um, resistance measurements are down here, and each one has a range associated with it. So um, let's get a resistor and of a known value and try to measure it. Okay. So let's bring the full bench now. Okay. So we have our packages. We have our packages of resistors here, and let's use the bigger ones. So in this package, I'm going to use 1K ohms, and then I'm going to compare that with 100K ohms. Okay. So remember, these things are in these packages, so I'm just going to use some scissors to clip out one of these 100K ohm resistors. And clip out a 1K ohm resistor. So there we go. Okay, so most folks are tempted to take the voltmeter, and I do this myself. If all I want is an approximate value, I'm gonna widen that out a bit. Okay, so if I want an approximate value, I hold one end of the resistor to the negative side and the other end of the resistor to the positive side, and then I look at my meter and it says 1.0. Okay, so let's brighten that up a bit. Okay, so it says 1.0, and I'm on this 200K range. What happens if I turn this down to 20K? Now it says 0.99. What if I turn it down to 2000? Now it says 993. So you see the precision of the measurement gets better and better as it gets smaller. However, if I turn it down to 200, now I get nothing. Now it just says 1, okay? And the reason is because my resistor is a 1K ohm resistor, and I'm measuring it on a 200 ohm scale. So it's much bigger than the scale, so it won't register. So now 1K ohms is smaller than 2000 ohms, and so here it will register, and I have 3 digits of precision. So now this goes between 993 and 994. 993. It's holding at 993. Okay, so I'm going to write that down here so I don't forget. And I'm going to take my resistor, and I'm going to insert it in the breadboard across the void. So what do I mean by the void? The void is this center part here. So when I cross the void, means I put one end in one side and one end in the other side. That guarantees that the two sides will not be connected to each other, but they will be connected to these buses. So I can plug anything in to one of these buses, any wire into one of these buses, and that will connect to this side of the resistor. And if I connect the wire, if I put a wire in any one of these holes, it will connect to this side of the resistor. Okay, so this is the one that I measured as 993 in my hand. Okay, so this is in my hand. And let's do the same thing with 100 k ohms. So this is my 100 k ohm resistor. So um, where do I need to turn this knob? I need to turn this to 200k. It's not going to register at 20k. It will register at 200k. And if I moved it to 20 megs, I would still be able to measure the resistance, but I wouldn't have the same amount of precision. So, okay, 200k ohms. Put the resistor in there and it says, well, it's varying quite a bit, isn't it? I've got to be really still. $100.1. That's what I'm gonna call it, 100.1. And that's k ohms. So this is 993 ohms. So look again. I have this in here. Because I'm on the 200k ohm range, that means that my resistance is going to be in k ohms. Okay, so that's now it says 99.9, 99.8. So this is the problem with handling this, doing this in your hands. It's going to change all over the place. Now watch what happens. So I'm going to plug this into my breadboard. Let's zoom in a little bit. Okay. So there's my two resistors, and you can see my voltmeter, and so this resistor here is my 1k ohm. This resistor here is my 100k ohm. So let's first go shift this down to 2000 and measure the 1000 ohm resistor. So now I'm putting the probe right there against the metal of the resistor like I had it in my hand, only now it's directly against the metal of the resistor. And I'm going to do the same thing here. And so that says 993. It's basically what we had before, 993. So I'm going to write that down, 993 in the breadboard. Okay, now this is the 100k ohm resistor. So I'm going to again put these probes in the holes, not deep in the holes, but just so that they're secure against the resistor. And oh, my meter doesn't say anything because I'm not in the correct range. So I need to turn this up to 200k ohms and now put it in. And now this says 99.9. So sometimes I do the experiments and they don't work out the way I want them to, and this is one of them. So just to try and get the result that I was expecting, I'm gonna put this 100k ohm resistor in there with my hand. Oh my goodness. Look what it says. Now it's bouncing all over the place and it's like in the 80Ks. So what changed? So, so when we measured it by hand before, it was 100.1 k ohms. When we measured it in the breadboard, it was 99.9 k ohms stable. So let's go back and look at it one more time in the breadboard. So now it's saying 99.7, but it's not bouncing around, and that's the main thing. Okay, so the first time we measured it, it was 99.9. Now it's 99.7K. The first time we measured in my hands it was 100K, and then I'm gonna just say guesstify that it was like around 82 k ohms when I did it the second time. So what's happened? Well, it's gotten a little bit warmer in my room here, and my hands are a little bit more sweaty than they were when I first measured it, and so my body basically is being put in the circuit when my hands are there. In fact, I may be able to emulate this by putting the probes on the component like that, and you see it says 99.8, and then I'll touch my fingers to the probes. Oh, and you see it goes down. You see it's all over the place. So having your body in the circuit, so here's the message. Having your body in the circuit is not a good idea. And you won't get precise measurements that way. So when we take the body out of the circuit, things work a lot better. So let's do it that way. Okay, so this video is getting a little long, so I think I'm going to end it right here. I think we met our goals except for building the circuit. So let's go back. So yeah, so we downloaded and installed the waveform software. We came across a problem, but we fixed that to see that it works with our computer. We used the multimeter to measure resistance and to measure voltage, and the two things we need to or that are left to do is to build a series circuit and test it. And so we'll do that in the next video, and then you will have seen everything you need to see to be able to do this lab on your own, in your home or your dorm room or in the lab, um, um, by just following along with what I've done, and hopefully you'll learn something. I do want to emphasize one more thing before we end this, and that is that the way the breadboard works, because um, some students have difficulty understanding, or from week to week forget how the breadboard works. And I just want to reinforce that once now, and I'll reinforce that every time. So these rows of connections here are all connected together. All of these 1, 2, 3, 4, 5 points are connected together, but they are not connected to these 5 points here. 1, 2, 3, 4, 5. And those are not connected to these 1, 2, 3, 4, 5. Okay, so anytime I want to make a connection to the end of this resistor, I can do it by plugging a wire in one of these holes, and it doesn't matter whether it's that one or that one or that one or that one. I'm always connecting to that end of the resistor. Okay, if I want to make a connection to the other side of the resistor, I can do that. Now there's another way, so this is with the resistor oriented horizontally and crossing the void. But I can take this other resistor and I can orient it vertically. So in one hole there, and in another hole there like that. So now this and the top end of the resistor, I can connect to that with any of these horizontally oriented holes, but not this one. This one doesn't connect. This one connects. This doesn't connect. This one connects. Okay? And for the other side of the resistor, this connects to the resistor, but this yellow one does not connect to that end of the resistor. Okay? So if you want to connect two things together, so if I wanted to connect these two resistors together, at one point they're connected together here, but they're not connected together here. Okay? Connected together here, but not here. So the symbol for a resistor is a squiggly thing. And so essentially we have these two resistors connected together like that, whereas the horizontal one is the 100K. And the vertical one is the 1K ohm. Okay? All right. So this is important to remember the way the breadboard works, because if you don't build your circuits right, you're not going to get reasonable lab results. And that's why when you leave the lab, when you're done with the lab, you really have to show me your results, because if you have a data table full of zeros, there's something really wrong. Okay? All right. So so we'll talk more about the way the breadboard works in the next video, and we'll do a lab where we make some measurements, and we'll have some fun with some of the other components that are part of the kit. Okay. All right. Thanks very much for watching, and we'll see you in the next one.